I'm Roy Clark, professor here at the University of Michigan and co-host of this event. Today it's my great pleasure to introduce my colleague, Professor Jens Christian Meiners of the U of M's Biophysics Department. Chris earned his undergraduate and doctoral degrees at the University of Konstanz in Germany and joined the physics faculty here at Michigan after postdoctoral studies at Caltech. Shortly after the biophysics program became a fully fledged department about 10 years ago, Chris was appointed chair of that new department and was responsible for putting together a brand new undergraduate program for biophysics and completely redesigning its graduate curriculum, and it was a huge success. So congratulations on that. Chris is a leader in researching living systems from a physical science perspective, including the mechanics of the different processes involved. And most recently, he has been interested in studying how decompression gas bubbles, known as the bends, can damage spinal cord tissue, and this is a very important development in, obviously, for the physics of diving, and in understanding the basic mechanism of what the bends can do. He's the recipient of the Harold Early Research Award and the Alfred P. Sloan Foundation Fellowship Award, and in 2019 he received a special award from the diving community, namely the Hamilton Award from the Divers Alert Network, and he's going to talk about some of that work this morning. I was really delighted when Chris agreed to give a talk on the life aquatic, which happens to be one of my favorite recreational activities. And I'm going to call on the audience, both the audience here in this room and also the remote audience, which is being live streamed, to submit questions which the speaker will be happy to address after the lecture, either online by email at this address, physics@umich.edu, or just write them on a card if you're in the live audience today. Now, without further ado, let's welcome Chris, and please take it away.
Thank you very much for the introduction, Roy. It's my pleasure to be here back in person. This is the first lecture that I'm actually giving live again. So great to see faces again instead of just looking into the webcam. So I'm excited about that. And I'm doubly excited because I get to talk about two passions of mine in one talk. One is the science. My scientific interest is about figuring out what's the role of mechanics in biology and to some extent also medicine. So for the most part of my career, I've looked really at the molecular and cellular scale, answering questions like, can mechanical tension in the DNA turn genes on and off, and so on. And now more recently, I also got interested in tissue mechanics, and the tissue mechanics project is related to scuba diving, which is my hobby, my other passion. I'm an avid diver, really enjoy everything underwater, from here our shipwrecks in the Great Lakes, which are beautiful. There are over 1,000 known shipwrecks around here, to the caves in Mexico, where I spend whenever I can get away some time there underwater, beautiful structures there. So two things here in one that I can talk about. And before we splash, how many of you have actually done any scuba diving? Wow, okay, about half of you. So for you, I hope I will tell you a little bit more about the science of diving and decompression sickness, which I hope you'll never ever need to ever get, and put some of the things that you might have learned in your diving courses in context a little bit, in the scientific context. And for those of you who have no experience with diving whatsoever, I hope I'm not going to turn you off from ever trying scuba diving by talking about one of the potential risks of the activity. Overall, it's quite safe as long as you know what you're doing. So with that, let me get started, tell you a little bit about what do we mean when we talk about decompression. So decompression, that's a rapid drop of the ambient pressure in whatever environment you're in. Diving is probably the most common context in which that happens. When you're at depth, you experience a larger pressure than at the surface, and we'll get into this a little bit more in the next few minutes. But there are other scenarios where that happens as well. High-altitude aerospace operations is one of those, and that's why NASA is interested in this topic as well. For instance, spacesuits are pressurized only to about 1/3 of an atmosphere, but the pressure in the space station is the same as here on Earth, so you have a drop of 2/3, a pressure drop of 2/3 of the pressure once the astronaut locks out and does a spacewalk. So that's a big decompression thing right there. Then another example, and that's historically probably the most important one, is caisson construction. That's a construction technique in which you have basically an enclosure, and you pressurize that enclosure to keep water out. So that was, for instance, how the Brooklyn Bridge was built. So the workers are actually down there. This is the third picture. Let me see if I can get the laser pointer here. So here, this is a picture of how the Brooklyn Bridge was built. So you have this, basically a cavern here. It's pressurized to 2 to 3 atmospheres from the top side to keep the water of the East River out. And when this was done, actually it was noticed a lot of those workers got sick. And initially, back then, it was first ascribed to, oh, well, just the working conditions. It's cold down there, hard work for the entire shift. But eventually, it was realized it had actually something to do with getting up from 2.5 atmospheres or so down here to atmospheric pressure very rapidly. And so that's what we know as decompression illness. So excessive decompression can lead to physical symptoms. So, what are those symptoms? There we go. It's a very complex mix of symptoms. You may have some, rarely anyone has all of them, but very common are neurological problems, anything from a tingling in your fingers to, in extreme cases, paralysis, pulmonary symptoms, shortness of breath, joint pain is also very common, skin rashes, and many more things. So it's a very complex set of symptoms, and actually decompression sickness is fairly hard to diagnose accurately clinically. It's usually done, well, you came up too fast, so chances are that you probably have the bends. And, but because these symptoms are also so common otherwise, so it's often, oh, well, maybe I just hurt myself, hurt my shoulder carrying my tank or something like that. And that is actually a bit of a problem that there's no single good test for whether you actually have decompression sickness or not. So let's talk a little bit about pressure at depth here, what your body is experiencing there. And starting point here is, well, the pressure that your body experiences increases with depth. So let me show this here in a very simple experiment. We have a water column here. this water column just about a meter here, and you'll see that just across this water column here, there's a substantial pressure difference. So I have here 3 orifices that I can open, and you can see already how the water pressure increases here from top to bottom and shooting out faster and faster as we get lower here in the water column. So pressure increases quite rapidly with increasing depth. And, well, how much does it increase? Well, here at the surface, we have 1 atmosphere of pressure. As you start going down deeper and deeper, every 10 meters, you add 1 atmosphere to the pressure that your body experiences here. And how much is now 1 atmosphere? Well, 1 atmosphere, that's also known as 14.7 pounds per square inch. To visualize this a little bit, this is a steel bar here that weighs 14.7 pounds, has a cross-section of 1 square inch, and it is heavy. It is a lot of pressure here on my hand right now, and that's just 1 atmosphere. And you get 1 atmosphere every 10 meters, so limit of recreational diving is about 40 meters, so you have 1 atmosphere from the air, plus another 4 of those from the water on you. So that's a lot of pressure. And what are the consequences of this? The first one is that air spaces shrink. So if you have an airspace, in particular your lungs, and you compress that airspace, what's going to happen is it's going to shrink. And for that, we have another little experiment here that I can show you. So here we have a diver with a little bit of an, yeah, we can get the, maybe, not coming on. Nope. Wrong one. Yes. So we have a little diver here, and there's a bit of an airspace here at the top. And what I can do now is add pressure here to my water column just by compressing the air top side. And what's going to happen is the airspace here in my diver's lung is going to shrink. I don't even need to apply very much pressure here. And what's going to happen is you see the airspace shrinking, and because of that, he even loses buoyancy and just dives down there. So just compressing the airspace here a little bit can have some fairly substantial effects here. And this was just me squeezing a little tube here. If we now go down here to, let's say, 40 meters, then we add here so we add another 4 atmospheres to it, and the effect of shrinking the airspace becomes very substantial. So at 4 atmospheres, at 4 atmospheres, the airspace is only a quarter of what it's actually at the surface. So airspaces shrink very dramatically. And that would, at least in principle, preclude diving because your lungs can't really work against such big pressures. And that's why we actually need to breathe compressed air. If you try to do this with a snorkel, just atmospheric pressure, about a meter or so would be the limit what your lungs can actually, the force that your lungs can actually generate. So that's not going to work. We are actually breathing, for that reason, compressed air to fill those air spaces back up with a pressure that corresponds to your depth here. So you're here at 30 meters, you would be breathing air that's compressed to absolute pressure of 4 atmospheres or 3 atmospheres above atmospheric. So that's how that part works. And now, what does that actually mean for our lungs, that the size of the airspace is so sensitive to depth? So if we look at that, if we are down there at the bottom of, let's say, Lake Huron, and fill our lungs then with compressed air, let's say 4 or 5 atmospheres, and we are starting to ascend, then what's going to happen is the gas spaces expand. That means your lung volume expands. And if you don't do anything, if you keep all the gas inside your lungs, don't exhale anything while you ascend, well, what's going to happen is the lung will become overpressurized, so you have more gas pressure inside your lung compared to the external pressure. And well, what's going to happen then? Your lung is actually made up of these very small alveoli, very small sacs here that facilitate the gas exchange between the air side and your bloodstream. And well, when you pressurize these very, very sensitive alveoli, let me show you what's going to happen then. So first, let's get this one. So we decompress the outside, so that's the equivalent of the ascent. The pressure on the external pressure, so the pressure inside the lung goes down. And so I'm simulating this here with a vacuum pump. And our marshmallow, this is your lung tissue or the alveoli. So the marshmallow has all these little bubbles here in them. So I'm reducing the external pressure on the alveoli, and they shrink some more, and then eventually they burst. So what you just saw there is first they expand, they burst. And then now I can even show you that they have really burst. If I let the air back in, equilibrate everything, your lung has just collapsed. So this here is now equivalent of a total collapse of the lung. That can happen in extreme cases. Usually it doesn't. More likely is that actually you have now some of these little alveoli here ruptured, and that means now gas can actually get from your lung into the bloodstream on the arterial side of your bloodstream. And that's a bad thing. So once you have these little gas bubbles inside the arterial side of your bloodstream, so they go then through your heart, and then get eventually pumped into the brain, and a bubble can get stuck there. And what happens when a bubble gets stuck in a blood vessel in the brain? That means you have a stroke, and that's one of the bigger dangers there. So from a rapid ascent, a stroke is one of the big risks here because of this mechanism. You rupture some of your alveoli, gas bubbles get into the brain and cause a stroke there. This may sound all very, very bad, but the good thing is there's an easy way around this, and it just means don't hold your breath when you ascend, and it's not going to happen. So this is just the thing of it doesn't happen very often as long as you're careful about how you dive. So that's sort of the direct effects of pressure. We can rupture our lung that way and get gas bubbles into the bloodstream. But there's also a somewhat more subtle effect, and that's tissue saturation. That's dependent on gas pressure. So again, here this is our alveolar, and we already know what it does. It generally, under physiological conditions, oxygen from the air gets dissolved in the blood, gets carried through your body, metabolized and into carbon dioxide, and then you get the carbon dioxide back out, and the carbon dioxide is then transferred out here into your lung and exhaled. So that's sort of basic physiology, but there's also another gas that we usually don't worry about in ordinary physiology, and that's the nitrogen. Nitrogen is inert. So as long as we just stay here at ordinary room pressure or at any constant pressure, the amount of nitrogen doesn't change when it goes through your body. So it just stays here at equilibrium. Some diffuses out, but the same amount diffuses back in, and it's just there. That's what ordinarily happens. Now, when you dive here, going from this situation here, nitrogen here in the air, in equilibrium with nitrogen in the blood, when you dive now, you're starting to compress the air. You're breathing compressed air here. So we have the compressed air, and now some of that diffuses into the blood and saturates the blood at your new pressure level. And the concentration at which you get the saturation is proportional to the pressure. So now all of a sudden you have 4 or 5 times as much nitrogen in your bloodstream than you had before. And that alone doesn't really pose a problem. Everything is fine again, everything is in equilibrium, nitrogen doesn't do much physiologically, so generally no issue while you're at depth. But now you come up, and you have all your nitrogen dissolved here, but the partial pressure of the nitrogen up here at the surface is much lower. So you have an excess nitrogen in your blood, and that has to come out somehow. And this excess nitrogen, by the way, that's called a supersaturation. So we have a supersaturated liquid here. And nitrogen has to come out, and ideally it would do it exactly the same way as it came in. So extra nitrogen is just diffused out here through the alveoli and eventually exhaled. So that's ideally what would happen. But there's also another mechanism that can happen, and that is this nitrogen, this dissolved nitrogen, can also come out as bubbles, so can form bubbles in the blood. And you probably all know what's going to happen now. We have here, instead of nitrogen, we have carbon dioxide. In there, carbon dioxide is actually very soluble in water. So if I have my can here and shake it, oops, let me see. So those are the bubbles, and that's what can happen with your blood if you get into that situation where you are not exhaling the nitrogen properly. So not a good situation. So next, I would like to talk a little bit about what these bubbles actually now do in your body when you get them. We already had briefly mentioned the stroke that you can get, but it's fortunately not quite as severe as that generally. The first thing to know there is decompression bubbles almost always form on every single dive, and they form on the venous side of your bloodstream. Why is that? Well, the blood pressure is lower on the venous side than on the arterial side, so the pressure difference is bigger, the supersaturation is bigger on the venous side, so that's where the bubbles generally form. And we can see this in ultrasound images. So here's an ultrasound image of the right side of the heart up there. And what you can see there is lots of bubbles in the heart, and that happens even on very benign dives. It's just a matter of fact. You will have bubbles in your bloodstream, except for the most shallowest, shortest dives, but generally you will have bubbles there. And well, we already heard earlier, bubbles in the bloodstream is bad, stroke for instance. Why are we not having a stroke every single time we go diving? Well, the thing is, the lung provides a very effective filter for those bubbles. So the venous blood here gets pumped from the right side of the heart through the lung, and then the lung, because it really facilitates gas exchange, it is able to effectively basically break up the bubbles and exhale that gas. So some bubbles on the venous side here is not an issue really, happens every single time. But when things get problematic is when you start overwhelming this filter here, then you can get some into the arterial side, and then we get back to the issues that I already mentioned. Another complication is there is a heart abnormality where you have a small shunt here between the left and the right side. That's another way how bubbles can get into the arterial side and cause problems. So bubbles alone, generally not the biggest problem that we are worried about. Let me briefly talk about one other, where is my clicker here? So briefly, this wouldn't be a physics lecture if I wouldn't put at least a little bit of an equation in there. And so let me very quickly tell you about how these bubbles now actually grow when you go through ascent and increase supersaturation. They mostly grow through diffusion, so gas molecules can diffuse into a small seed bubble here. And I don't want to drag you through this, but we can easily calculate how much the amount of gas in the bubble changes here as a function with time. The NDT is something that's proportional to the bubble radius. That's actually quite notable. You would think it's proportional to the surface of the bubble, the amount of gas that you can get in, but it's actually, if you do the calculation, just proportional to the radius. We also have the ideal gas law. Nothing special there for those of you who have had a little bit of physics or physical chemistry. We can lump those two things together, get a differential equation where amount of gas in the bubble is proportional to the third root of, change in amount of gas is proportional to the third root of the amount of gas in there. And then we can calculate what we get. And the main story here is it doesn't really matter how big your seed bubble is, as long as you have some kind of seed bubble. After about a minute or two, they reach sizes here where they become problematic, assuming here in the moment a pressure difference of 3 atmospheres, so popping up from 100 feet down or so. So a relatively quick process over minutes, and you get some very substantial gas bubbles here. So enough of the math. Let's go back to bubbles. Now the question of what's happening if these bubbles don't form in the bloodstream, but if they form in actual tissues. And the most problematic one there clearly is the spinal cord tissue, because that's really, where the neurological symptoms can arise from. If it happens in a muscle or so, not such a big deal, but nervous tissue, spinal cord, that's where it matters. So again, we start out with a little seed bubble in equilibrium with the external pressure here at first, and gas, the black dots here, dissolved in the tissue. Now, we have our rapid ascent, and the first thing that happens is this pressure balance is thrown off. We have less external pressure than before, and that means just by expanding gas spaces, the bubble expands instantaneously. But now, unlike in the bloodstream, the tissue itself, it's an elastic material, it opposes that growth, and eventually you reach some equilibrium here where this elastic force from the tissue together with the internal pressure of the bubble balance the external pressure. So that here happens almost instantaneously up to here. And then a slower process kicks in, and that's diffusion. We already talked about diffusion into the bubble. So that's that process here. Bubble accretes gas from the tissue here. But then there's also diffusion out of the tissue here into your bloodstream. And that is actually a fairly slow process. So at first, the bubble will accrete here gas. And then eventually, the tissue here will lose the gas to the bloodstream, and the bubble will shrink down to some new equilibrium. And just to show how slow diffusion actually is, if I can get that image here. So what I did here, I made a gel as a phantom for a tissue, a bit of agarose, so 99% water, 1% agarose here, and I put it back in there. And this morning at around 7 o'clock, I injected a little drop of food dye into it, and now it has spread to a couple of millimeters. So this gives you sort of an idea how fast or how slow diffusion is. So to get the gas out of your tissue here, that takes typically hours, just to put the time scales here in perspective. So you have a fairly quick growth of the bubble here over minutes, and then for the new equilibrium, this here can take hours, or in some very slow tissues, even days to get fully all of that out there. So that's what's happening, at least schematically, in tissues. And a few years ago, I got interested in, can we actually check that experimentally? I needed a small project for our MSci Academies here, a program where we have incoming freshmen participating in small research projects from day one. And so what we did there was making a gel very much like this here, compressed it to 4 atmospheres absolute, and let it sit there overnight under pressure that it really gets saturated with all the nitrogen, and then decompressed it very rapidly to atmospheric pressure. And this video, and took then with a microscope a video of it. This video here is sped up 60 times, so 1 second in the video is about 1 minute in real time. And so we got these kind of videos out of it, and noticed 2 things here. So first, yes, the time scale is good, so no big surprise there. The other thing that we saw there is also that the bubble sizes are fairly homogeneous. So if I pause this video here for a second, yeah. So if I pause it for a moment here, the sizes, ordinarily when you think of sort of random bubbles forming, you would think we have lots of big ones, small ones, everything in between, but the size distribution is very homogeneous. And that's basically what I already showed you in this little calculation there. The initial bubble size didn't matter. Everything in the end came back onto this one diagonal line there. So that's pretty good. And then the one thing that really surprised us was the shape of these things. All these bubbles look like these lentil shapes here, and with fairly sharp cusps at the end. And that was inconsistent with basically any simple mechanical model that you make. And what this was actually telling us, when you see something like this in material science, the first thing you think of there is fracture, cracking. So the mechanical force from this expanding bubble is actually cracking our gel apart, breaking it apart. It's no longer an elastic expansion. So elastic expansion, that was what I had there earlier in my simple model. Think of a balloon. You can inflate it as many times as you want it. When you reduce the pressure or increase the pressure, it always goes back to the same size. But this here is different. So here we actually get real cracks in the gel here. So we are not seeing just an elastic deformation. We are actually seeing here fracture, tearing of the gel. And, well, when we saw that, of course, the question was, does that happen in actual biological tissues as well? So, what we did was we went to a model system, to spinal cords of cows. And we picked that model system because the mechanical properties actually of bovine spinal cords are reasonably similar to those of humans. And also we had easy access to them. We just went to a local meat processor and asked them, next time you butcher some cows, can you give us a spinal cord from a cow? And we got that way also around all the animal issues that you would otherwise have. So we got a couple of these spinal cord samples. Now we still had to image them, and we couldn't just use a microscope anymore because, well, it's not transparent, these tissues. So we went to North Campus, to the biomedical engineering department. They have a high-resolution small animal MRI scanner, 7 Tesla MRI scanner that we could use. And we built a pressure cell, a pressure chamber that actually fits into the MRI scanner and is compatible with these high magnetic fields. And did basically the same experiment that I just showed you with the gel, now with bovine spinal cord inside the MRI scanner, and compressed our spinal cord here for 2 days to 6 atmospheres, and then rapidly reduced it and scanned and looked at various time points here. These are here cross-sections that we take, and we see these bubbles springing up. And that was, of course, quite exciting, actually seeing these bubbles grow in real time. That's something you usually don't have access to most of the time in the literature. When you see about bubbles in tissues, it's always later than histopathology or so, cross-sections much after the fact. So we could actually see them grow in real time here. And you can imagine having a bubble like this in your spinal cord is definitely not a good thing. So now we started to look into, well, is this again tearing like what we saw in the gels, or is it elastic deformation? And in this case, the shape didn't tell us a whole lot. It's such an anisotropic tissue, so inhomogeneous, we couldn't really tell much from the shapes of these bubbles. So we devised a different kind of experiment. So what we now did was we, again, compressed the spinal cord here, saturated it with nitrogen for 2 days, and then reduced the pressure only by half. So just enough that we get small bubbles, and again waited for equilibrium. So now we have small bubbles, these seed bubbles in a way that I talked about earlier. And those we can actually see here. So in line A here, we found a bubble here. And then what we did at that point was we wanted to probe the mechanical properties, the mechanical interaction of the bubble with the surrounding tissue. Is it tearing it, or is it just elastically deforming it? And we did that by very briefly decompressing it to 1 atmosphere and recompressing it, 5 seconds. So very quick reduction in pressure, increase in pressure again. If it's completely elastic, it would always return to the same size. But if it actually fractures the local tissue, rips the tissue there locally, then what's going to happen is the space that the bubble has available increases and it gets larger in each time. And that's actually what we see here. So after the first cycle here, the original bubble here is marked in red. After the first cycle, you see already a little bit of a black rim, then it gets bigger, bigger, and bigger, and then we decompress all together here in the last one, then it gets really, really big. Now you actually have this ideal gas law effect, the expansion, on top of just the increase here from fracturing the material. So at this point, we are quite confident to say, at least we are seeing here, some kind of irreversible deformation, not just elastic behavior. And that now brings me, was something we wanted to understand also quantitatively a little better. I mean, the bubbles, the other math worked out so nicely. Can we do something like this here? Well, here it gets really complicated, and we actually went to computer modeling instead. So what we did was build a finite element model of the spinal cord by taking our MRI images here and basically making a small, subdividing in small little pieces here, a network, a mesh network of little springs, and then looked at the elastic response, what happens when we place a bubble in there and start expanding it. And what we get there is, if we go like in the experiment before, from 3 atmospheres to 1 atmosphere, and assume an elastic medium, what we get is stress inside the spinal cord here, very localized around the bubble. So the stress in the material doesn't go very far. It's very highly localized around the bubble. And also, we can get some numbers out of it if we put the material parameters in that we know for the spinal cord tissue. And we can see we can easily exceed the yield stress, so the stress that's known to actually tear nerve tissue apart. We can easily exceed that several-fold here. So we have good reason at this point to believe, yes, the mechanics is there. An expanding gas bubble in the spinal cord is not just an elastic deformation. It is actually, in a way, a traumatic injury, an actual injury, a cutting of the spinal cord that's happening there. So what about treating all of this? Standard treatment is recompression inside a pressure chamber. So if you get a DCS hit, what they do is they put you into one of these pressure chambers. This one is a really, really big one. Most of them are actually very, very smaller than that. And compress you typically to somewhere around 2.5 atmospheres absolute. So here, then they give you pure oxygen and occasionally switch to air. And such a treatment takes a couple of hours typically. So this is one that was developed and still used by the US Navy. This does 2 things. So one is the pressure effect, basically reversing what I've shown you in this idealized graph earlier, so of just compressing externally everything so the bubble shrinks. And the other thing with the oxygen, that is now also pulling the gas out there. Oxygen gets metabolized, doesn't contribute to bubble growth, so the nitrogen pressure on the outside is 0 then, and so all the nitrogen can diffuse out. And that's really the aim of all of this, is dissolve the bubble. And that's certainly good and important, but with what we have seen, we asked ourselves also, shouldn't we really also treat this like a traumatic spinal cord injury? So like little paper cuts in your spinal cord in a way. Then this, and the belief that we need to do this is also bolstered by some of the clinical observations there. So one of them is that surface oxygen so oxygen, normobaric oxygen at atmospheric pressure as a treatment is only partially effective. That's usually the first thing you get when you get a decompression sickness hit or so on a boat or so. The first thing they do is give you 100% oxygen. And with the math that we've done, the bubble math, we would think that probably about 2 hours or so on pure oxygen would dissolve any bubble pretty much outright. So, but it's known it's only partially effective. It briefly reduces the symptoms a little bit, but everything comes right back when you go off the oxygen. You need the recompression treatment really to make it work. And the other thing that's clinically known is that the initial treatment is very effective when you get it right away. That means within the next hour or two. But then when you come in the next day or so, effectiveness goes down dramatically. And even worse, what they do actually then is if it doesn't help, let's say you get the treatment 2 days later, if it doesn't help, they tell you, come back next day, we do it again, come back next day, they do it again. And that is something, based on what we have seen, may not be the best thing to do. So can these additional chamber treatments perhaps exacerbate the damage here? In a way, that's what we have done here in our experiments. Each time we compressed and recompressed our bubble, our spinal cord tissue, every single time we did that, the damage got bigger to the spinal cord. So maybe that's not really a good way to go about it. And related to this is the question of buildup of scar tissue there. So if you think of this as a wound, as a cut, if you have that, well, what's the first thing you do usually? You compress it, and then you keep it compressed. You stitch it together that it heals well. And this here, every day, oh, has it healed yet? Has it healed yet? You can imagine that's not a good thing to do. You build up scar tissue there. And what that does is then also increases the propensity for future decompression sickness hits after you have been treated for the first one. And this is only anecdotal evidence. It's very, very hard to really get hard data on this one. So please don't mistake this as data. It's an anecdotal evidence, but there are a good number of those cases. So here's one that I know personally, highly experienced technical diving instructor, did a dive, not particularly deep, just 22 meters, but for about 2 hours on a gas mix that had less nitrogen in there, so actually less tissue loading, less nitrogen in the tissue than you would get when you dive on air. By all diving algorithms or so, he was very much on the safe side. He had something like 8 minutes of decompression obligation by the standard algorithms to get enough gas out of the body to safely surface. He ascended already so slowly that basically there was no tissue loading left, and then even played around in shallow water even longer. So by all intents and purposes, he should be completely fine, but he got a neurological DCS hit. And mostly shoulder pain, plus some other neurological symptoms. And of course, well, experienced instructor, oh, I'm not getting bent. No way this can happen. So what he did was he did not go to the next recompression chamber right away. He went home and just thought, oh, well, yeah, this shoulder pain, oh, this is just hauling the tanks around, or maybe exercise the day before. But eventually he finally realized he probably had to go in. First put himself on oxygen, temporary symptom relief, and then at the chamber he needed 4 treatments in 4 successive days. Then symptoms were gone. And he thought then, oh well, a month later or so, let's do a few very shallow dives. The first few were okay, and then bang, came back in exactly the same spot, serious pain in the same spot, same kind of symptoms again. Got another 4 chamber treatments. And then this time he decided to stay out of the water for half a year, came back, 5th dive again, very shallow, nothing really to there, and same symptoms again. So 6 months later, in exactly the same spot. So the spot there, in some ways, remembered where he got the first hit. And that would be consistent with our hypothesis here of scar tissue built up from really a traumatic injury, some kind of cutting injury in the spinal cord there. This is something, of course, in the moment, this is all anecdotal. Much of it is speculation, so I cannot make a medical recommendation to change the treatment tables here, but I do think these repeated treatments may be more problematic than they are good in some of those cases. So let me go to the last point that I would like to make. I've talked quite a bit about that we need some kind of seed bubble to get this bubble growth process going. So where are those seed bubbles coming from? They cannot spontaneously form. If you get supersaturation in pure water, there is no, under these pressures, there's no way that it can spontaneously bubble. You need to have fluctuations that are large enough in pure water, just thermal fluctuations, density fluctuations there. You would have to go to a supersaturation that would correspond to diving to the depth of the Mariana Trench. So you don't do that. And so out of question here, not happening. So something else has to nucleate the bubbles. And bubble nucleation is, of course, quite well known. You can think of a champagne glass here, for instance. You have your champagne, and then what happens is here you nucleate the bubbles. And that you need bubble nucleation, by the way, I can also show you with a Pepsi can here. Earlier you saw how that one really spilled all over the place. If I now open this one here, that is just sat here for a while, nothing happens, just a little. And both of them have the same amount of carbon dioxide dissolved in the liquid here. So the shaking doesn't dissolve anything more, and both of them were at equilibrium here. They have been sitting on the grocery store shelf for months or so. So all that's different here is we have small bubbles that I introduced here. We had seed bubbles that I introduced in the first one through shaking, and I don't have seed bubbles in the one that I just opened here. So that's the role of these seed bubbles here. You need them really to get it to bubble well. And yeah, champagne glass, how do you get your seed bubbles there? You usually have a rough surface. They actually grind a little piece here in the bottom of your champagne glass so that you get these nice streaks of bubbles in the champagne there. So rough surfaces do it, hydrophobic surfaces, but so far no one has come up with anything really good like that in the human body. So right now, most likely how we get these small seed bubbles to start is in turbulent flow. Turbulent flow means you have shear forces, quite a bit of shear forces there in your flow, and that can give this additional force that you need to get over this initial hump to form a bubble. You get so turbulent flow can actually induce very small bubbles. Where do you have turbulent flow? Most of the blood flow is laminar, so no turbulence in most of the blood flow, with the exception of heart and aorta. There you have actually turbulence. So speculation here in the moment is you generate very small seed bubbles in the turbulent flow in the heart and in the aorta, and then they get transported into the deeper tissues and eventually grow into big bubbles there when you get to the decompression part. So these bubbles here are constantly replenished through your circulation. And that's something we can also probe with our model gels here, a little bit at least. We prepared gels where we try to pull out all these seed bubbles, so by degassing the gel here first, and if we do that, we don't see any bubbles really springing up. And then the other thing that we did was we tried to really squash these little seed bubbles. And the way we did that, we poured the gel in the liquid form, compressed it very quickly while it was still liquid. And that then, again, basically eliminated all the seed bubbles. They were now really squished together through this initial compression. And that's now different from actual diving, because in diving, yes, you would squish these initial bubbles when you descend, but your circulation keeps going, keeps replenishing those little seed bubbles, and so you can't get rid of them. And that's really what's driving this then in the end here, why you are still getting these kind of bubbles. So, and that pretty much brings me to the end of what I'd like to present here. So in a nutshell here, I hope I've been able to convince you that human physiology is affected by pressure, in particular, pressure here, air pressure, what you're breathing there, and in particular this absorption of gas through Henry's law, dissolution of gas first in the blood and then into the tissue. And decompression sickness is not just one very simple mechanism, it's actually a fairly complex interplay here of physiology, the bubble formation mechanism, so some of the physics there, the bubble growth mechanisms, then the response of the surrounding medium here. I hope I've been able to convince you that mechanical response of the tissue here, of the spinal cord tissue, is really, really important. So fracturing the spinal cord tissue is what may be going on here in many, many cases. And that this can have potential consequences for how we treat these kind of illnesses. And physics, again, is helping us here to unravel all these complexities and hopefully guide this into the future. And with that, I'm reaching the acknowledgements here. I have a graduate student working on this, Roman Alvarado. He has been doing much of the experimental side there together with Cameron Hodges. He was a biophysics undergraduate major, graduate stayed another year at my lab before going into a clinical setting now, radiation safety director at a hospital. He has done the initial MRI imaging. Adrian Bari, a talented undergraduate, he did much of the gel work. Joan Greve, our collaborator in biomedical engineering. Osama Kashlan, a collaborator in neurosurgery, providing the medical expertise, and Josh Simmons, an undergraduate who did the finite element modeling. And I would also like to thank the Divers Alert Network. They have provided funding for this work. And finally, of course, thank you for your attention.
Well, thank you, Chris, for that great talk. I really appreciated all the technical detail there, and I'm sure that our audience did too. Some of those details raised a number of interesting questions, which I hope you'll be able to address.
You'll see.
I try to group these together a little bit during the lecture. There may be additional questions from the audience while we're speaking here, but let me start with a question to do with freediving. And that, maybe you can explain what freediving is, but the world record apparently has been reported as something like 400 feet or 120 meters. And how is that done? Actually, let's get the microphone. So how is freediving done, and what are the risks involved as far as decompression goes?
Okay, I'm not a freediver, so don't have that training. So how it's done, freediving, is without any scuba equipment. You just swim down, and some can do this to amazing depth. So the decompression risk there is basically not there because you're not introducing any additional nitrogen into the system. So yes, you have your initial lungful, but that's not that much, the nitrogen that you have in that one lungful. Yes, some of that will go into the tissue, but you're not keeping replenishing it. That's what you would do otherwise when you're on scuba, you keep replenishing it. And so that reduces just the amount of nitrogen that's available here that could get dissolved, and so you never get really into these supersaturation situations.
I remember you made a point about not holding your breath, and presumably free divers have to do that because they're going down so deep.
But then they are not filling up the lungs with the compressed air that you're getting from your regulator. So for them, yes, the lung volume shrinks, but it would never expand more than what it was at the surface because you're not pushing any additional gas into it.
Yeah. So that was an interesting question. And another question is to do with kind of aerospace applications where instead of diving down into the ocean, you may be going up into the atmosphere with a pressure decrease during the ascent of an aircraft, for example, or Jeff Bezos going up in a space module out to the edge of the atmosphere. What kind of pressures there are presumably the differentials are less than what you'd experience deep in the ocean, but what are the issues to do with aerospace?
Well, in most situations, you still have, you're pressurizing the capsule or the cabin. So on aircraft, the cabin is pressurized generally, not quite to 1 full atmosphere, but the drop is sufficiently low that you generally wouldn't have to worry about unless you have been diving before and you're already super saturated. Then that difference actually can make a difference. So if you have been diving, you have been loading up on nitrogen, and then go on a flight to whatever altitude, then that additional reduction in pressure can actually increase the supersaturation and cause decompression sickness there. But going from 1 atmosphere to whatever the cabin is pressurized to generally doesn't happen. Space capsules, the International Space Station is pressurized to 1 atmosphere, so they're really so while you're up there, nothing would happen. But again, extravehicular activities, spacesuit pressurized to about 1/3 of an atmosphere, 100% O2 though for that, to keep the oxygen partial pressure up. And that actually is an issue, so they have to decompress relatively slowly, at least under normal operation. But there's always the worry, of course, what do you do if you have to get out of this right now, everyone getting your spacesuit out or whatever, if something really goes really, really wrong. And then that's why NASA is worried about those type of scenarios, rapid pressure loss, those kind of things, and space debris hitting the space station and depressurizing it quickly. Then, yes, that's why NASA is interested in it.
Thank you. So we had a number of questions about the mechanics of diving. So one question that came in, which is quite interesting, is to do with the recovery of using pure oxygen after diving back to a depth of, say, 30 feet, which is about 1 atmosphere. Would that intermediate kind of step help with avoiding the bends or treating the bends?
Which I fully get
so
the
basically,
question.
it's from a deep dive up to an intermediate depth, and then waiting there.
Okay, yes.
I think that's a standard
yes, that's
procedure.
a standard procedure. That, so this is often called stage decompression or accelerated decompression on oxygen. The way how that goes is you dive deep, load up on nitrogen, and then come up in stages slowly. But as you've seen, the last 10 meters are the most critical ones because there you're going from 2 atmospheres to 1 atmosphere. That's really where much of the action is happening. And so what you do then is switch your breathing gas from whatever air or whatever you have been breathing at depth. You switch it over to 100% oxygen. And that has the advantage, now you have a partial pressure differential between your bubble. The bubble is now at 10 meters, so 2 atmospheres of pressure in the bubble, to nitrogen pressure outside is 0 now because you're 100% oxygen. So now you have artificially increased the gradient here, the concentration gradient, and you can wash out the nitrogen relatively faster, so typically about twice as fast as if you just did it on air or whatever your back gas is. So that way, yes, you can speed it up. It has other problems. Oxygen becomes toxic at higher pressures, so you have to, so 6 meters for 100% oxygen would be the limit. Anything lower than that, the additional oxygen would actually could cause problems, including I think it's mostly really, neurological problems. You would probably get a seizure or something like that. So this trick with the pure oxygen works for the very last bit of your dive, the last 6 meters or so, to speed up the decompression process there, and it's commonly done.
Thank you. So another question is, this is a classic kind of introductory physics question. How can our bodies operate in high pressures? And specifically the breathing mechanism.
The breathing mechanism works only when you breathe compressed air. You really have to have basically a balanced external pressure on your lung here on the outside and what's inside your lung. As soon as that pressure differential gets larger than something like 0.2 atmospheres or so, you just can't do it anymore. Your muscles can't really overcome this pressure differential anymore. So that's why you need to breathe compressed air at depth to compensate for that. You have to more or less balance it, otherwise the mechanics won't work.
I seem to remember that's one of Newton's laws.
All of that.
Action and reaction.
Yes.
Kind of physiological question. What's the cause of shoulder pain that was experienced by one of the diving cases there? Is that's a neurological condition?
It seems to have been. These things are very hard to diagnose, and of course I wasn't there, and I'm not a physician. But it's fairly common that you have you can pinch a nerve, and you know how that feels like, and this seems to be the kind of effect that they were feeling. That's all I can say there. It's fairly common, these kind of sort of stinging pain, again, like pinching a nerve, and but exactly the physiology there, I'm not a physician.
That's also in the muscles that have an imbalance in oxygen supply, I would imagine.
That, or it might just be even the nerve somewhere else getting pinched off. Let's say, even if you have, let's say, a bit in the spinal cord or so, you can have still symptoms further downstream. And so it's most likely, I guess, equivalent to a pinched nerve in some ways, what the experience there is.
And someone asked a question about how does this compare with altitude sickness? I think this is a different topic, but maybe you could say a few words about that.
So that's something that's been often sort of suggested offhand, and no one has ever really made a clear connection there. I don't think there's much there. So altitude sickness is typically something like when you climb a mountain relatively quickly. Most of the time it's headaches and so on, but it's still, everything is typically still slower than the differential nitrogen issues. So there's probably just, I think it's really just starving of oxygen. I think is really what the main effect is that you're seeing there. Just too little oxygen in the blood, and well, obviously your brain cells don't like that, and headache is the consequence there. So that's probably what's happening there. I don't think it has anything to do with the nitrogen side.
So this is a really nice question about the difference between DCS and nitrogen narcosis. And
Okay.
the related question is, why do whales not get DCS? I remember going in New Zealand to have a lecture on a boat and do some whale watching, and the depths were incredible. There were many thousands of feet. So what's going on with?
Okay, First, the nitrogen narcosis. I haven't talked about that at all. It's an unrelated issue. Nitrogen narcosis or the only relationship there is the excess nitrogen that you have can also get dissolved in the cell walls of your nerve cells and change the properties there. such that it induces a bit of narcosis. Most of the narcosis gases work that way. They get dissolved in the cell membrane of your nerve cells and change in still somewhat unknown ways how the receptors there work. And if you go to high nitrogen pressures, that's what's happening is you're dissolving nitrogen in those cell walls and they change some of the neuroreceptors there. And it is a completely reversible process. You just ascend a little bit and the effect is gone. The effect, by the way, is really sort of a narcotic effect. Depends a little bit on the situation and also on the person. What you exactly experience can be anything from feeling like a little bit stoned or so to also more scary anxiety type issues. So for me, it's warm water. It's sort of the nice and warm and fuzzy feeling. Cold water, for me, it's sort of, I forget a lot of things when I do a deep cold water dive. So amnesia is something I have a little bit. So anyway, this is solution of the nitrogen in the cell membrane of the nerve cells. Exactly how it affects then the receptors is not quite known. The whales, that's a good question, and people are still looking into it. They have looked at also genetically if there are differences in the various proteins that are involved here and so on. But I think it's still largely not quite settled why some mammals can dive so deep without any of those obvious effects. But what's actually known is even with some fish there are problems. So from people who collect fish for aquariums, they often have to bring the fish up through some intermediate steps, or so they can't just drag them out from depth, or they would just die. So there are some of those effects there as well.
Right. So another related question, or perhaps unrelated, is can oxygen supersaturate in the blood?
Yes, well, supersaturate probably not. You're metabolizing the oxygen. But for oxygen, there are two things here at play. One is exactly the same Henry's law mechanism. You get higher and higher oxygen pressures, more oxygen gets dissolved in the blood. But your oxygen also has hemoglobin in it, and that binds oxygen and transports it in. So for relatively lower oxygen concentrations, so here partial pressures like what we have here, 20.21 atmospheres or so, it's all the bound to hemoglobin, and there's almost no free oxygen in the blood. And if you go to higher oxygen concentrations, then you can actually start pushing some into the blood, and that's where the oxygen toxicity comes in there. Now this nice regulatory mechanism that all your hemoglobin is saturated, and that sort of limits how much oxygen you usually get into the tissues. That goes out of the window once you start really getting to these high pressures and pushing it into the blood itself, into the liquid. And that's where this toxicity comes from.
I find it very interesting that you made a connection between spinal cord injuries, which could be the result of accidents at work or lifting, and the damage caused by decompression sickness. As that, how is that field? Did you start that connection?
Yes,
it's
so
really
this is something I sort of brought up to someone in particular. That's why I have the neurosurgeon there as one of my collaborators. And so he thinks certainly this is very much a way of direction that we need to explore and think more about. The unfortunate part is right now when you have a traumatic spinal cord injury, let's say from a car accident, in the acute phase they can do very little for you. They could get any bone pieces or so out, sure, but otherwise there's really not much there they can do at the moment. And so even if we can prove that this is really a big mechanism here, we still wouldn't quite know what to do clinically at that moment, how to address the injury part. Although there might be something going in the other direction, can perhaps immediate recompression help in certain spinal cord injury cases where you have a gap or so that you could perhaps compress again. So that's in the moment sort of a bit of the speculation. Maybe there's something there we don't know yet at the moment.
Yeah, so the medical community is beginning to see the
Very
connection.
slowly.
That's really good.
As
Yeah.
it always goes when a physicist talks to the medical community.
As a, you know, what you talked about and biophysics in general is a highly interdisciplinary activity involving many different disciplines: chemistry, mechanics, biomechanics, medical issues, physiology. As an applied physicist, which you also are, I always ask the question, how can young people entering the field prepare themselves for this world of, accommodating all kinds of different ideas from different disciplines? What kind of preparation did you have in this? Well,
So there are many
what
ways.
do you recommend?
I think the most important part is just having the natural curiosity beyond your field. I think that's the most important part. Be curious about what's going on. If you have a problem that you'd like to solve, if you need some physics for it, learn the physics that you need, read up on the biology or whatever it is. Just be curious and don't just say, oh, I don't really know much about this area, I'm not going there, I stick with my specialization. So I think that's the biggest piece there. Be curious, be open-minded. Preparation, of course, a good science background is always helpful. I, of course, like the physics background, tell everyone physics is the thing to do. We sometimes say, yeah, physicists are the better engineers in applied physics, so a little bit like that. Physics helps. Easier to go from physics to biology and medicine than the other way around. So I was trained as a physicist and actually got into the bio side only during my postdoctoral studies, so fairly late. I know quite a few people who have done it that way, and relatively few who have managed to go the other way, let's say as biology majors, later go into physics. That seems to be rarer. And of course, now we have also these interdisciplinary programs like biophysics, biomedical engineering, and so on. So if you already know that that's the direction you'd like to go, those might be for you.
Well, Chris, thank you so much. This is a very illuminating talk, and I'm going to just call from the audience if there are any other remaining questions. I see one here. So let me bring the microphone.
Thank you. You talked about bubbles forming inside cells. And I'm curious, you talked about diffusion from the cell liquid into the bubble, but the partial pressure, I'm sorry?
Not inside cells, in the tissue, but not inside actual cells.
Okay, but it seems that since the bubble's probably pure nitrogen, the partial pressure would be 100%. So how would gas diffuse in? Because surely the partial pressure is lower outside the tissue than inside, outside the bubble inside.
No, actually in the tissue, you load the tissue up when you go deep. Let's say to the equivalent of 3 atmospheres, 4 atmospheres, or whatever. And now you come up, the bubble expands, so the size of the bubble goes up, and therefore the pressure in the bubble drops.
Oh, okay.
And now you have the gradient,
So
now
now
you treat it from the outside.
Okay, makes sense. Thank you.
If I've just been hired for a James Bond movie to fight underwater, and I'm involved in an aggressive action at 10 meters, how does that affect the decompression? Would that accelerate, or would that reduce the decompression requirements after an extended fight scene where I'm trying busily to do away with James Bond?
Yes. So, okay, if you try that and don't get shot underwater or anything, then the first thing that would happen is your risk for decompression sickness goes up dramatically. So you would like to basically hang there relatively still, have some very light movement just to keep the circulation going, not getting cold or those kind of things. But you definitely do not want to put strain or stress on any muscles. That's a known factor that leads to decompression incidents. So when you do your decompression stop and then do, oh yeah, I can already unhook my tank, do this or that while I'm waiting here, don't, is what we, that's a known factor there.
Well, if there are no more questions, I think that's all the ones that we received. Thank you very much, by the way, for all those interesting questions. And thanks again, Chris. That concludes the presentation for today, but I just want to take this opportunity to thank all of our loyal sponsors and supporters of Saturday Morning Physics. And we really appreciate your support continuing through fairly difficult times with the pandemics and all of that. I also want to express my appreciation for the demo lab staff, and I want to call out Monica over there, who's done such a wonderful job, and her staff. Thank you so much for all the marvelous demonstrations. Simple but very, very effective. And I want to also point out that we will be having our last lecture in the fall series in 2 weeks' time. And that lecture will be given by Dr. Oliver Kripgans from the Internal Medicine Department in the U of M hospital, and he's going to tell us all about the latest developments in ultrasound imaging and how the resolution of those images has been improving, and he's been one of the pioneers of methods to do that. And I noticed that you also had some, Chris, you also had some ultrasound images of bubbles, and that's one of the things that really comes out from the new ultrasound methods that are being used, is to be able to image things like that. So I'm going to wrap things up for today, and we will see you again in 2 weeks' time after Thanksgiving. Have a happy holiday, and let's thank Chris again.